Okay, hi everyone. So I'm Dr. Abdullah, and today we are going to be taking this session on the topic of electrical laws in action from theory to real world hardware. Okay, so in today's lecture, we're going to look at the fundamentals of electrical and electronics engineering. We're going to understand some of the basic concepts that it has and how it is governing our today's world. Okay, so we will be looking initially to the importance of these electrical laws and how the basic electrical circuits are governing everything. We'll see some of the major terminologies like voltages, currents, resistance, Ohm's law, power, Kirchhoff's law, stuff like that. And we'll be seeing some of the extra theory like series and parallel circuit combinations. We'll see some of the network theorems, and then afterwards we'll be seeing some of of the basic design, how the products are made, and ultimately we'll walk to that ending conclusions and question answer section. So let's dive into it. So the first question is, why do we need to study in electrical laws in the first place? Well, I believe that all of you probably have seen from time to time circuits like these in your life. So basically, all of the hardware technology that we use today, it is built by these electrical laws. Okay, so every technology, your laptop, your mobile phone, your PC, your device, even your AirPods, your hand-free, any kind of equipment that works on electricity is built on these laws. So we're going to look at those fundamental things. What are these? And we will see if there's going to come a day if AI can replace these laws. So I'll give you a short answer. The answer is no, uh, because these are physical, actual elements, and well, these will stay no matter how advanced we get in AI. AI can take any kind of job as well. But to build the technology, we would always need these laws and these circuits and the stuff that we use in this. Okay, so we'll just go ahead and see what does this foundation of electronics does in the first place. Well, it predicts the circuit's behavior. So let's understand what is a circuit. So a circuit is a device that has electronic components attached to it. Okay, so we can call this a circuit. So it has some components of electronics attached to it, and it is performing some kind of a task. Okay, so that is a very vague basic definition of a circuit. So if we have designed something using electronic components and it's working, it's doing something. So we are trying to change the channels of a TV, of a radio, of anything. So while doing some actions, we can predict what it is going to do. We can predict its behavior using the basic law. Okay, so that is mostly used for debugging purposes and, of course, the design process. Of course, they're not that much useful from user's perspective because the user is always only going to operate it. They can't fix it if it is broken. They are not going to design it in the first place. So if you want to fix it, need to know how it was designed. And if you want to design it, well, you need to understand these basic laws and see, uh, get your design from these things. So there's this picture on the right hand side is the final circuits that you might have somehow seen in your any kind of equipment that you might have opened in your life. So this is called a PCB, printed circuit board. So it has all these electrical components. So this comes at the final stage. The initial stage starts from a paper and a pencil. So we design these circuits with it has special symbols which represent some special things. We'll see some of these today. some of the basics ones that are always used everywhere. So we'll see how these circuit and these things represent some circuits and which actually do some real life tasks when we design them. Okay, so how does it work? How does it work? What's the process of this electrical engineering design? So firstly, you get an idea. Maybe you say, okay, I want to build a circuit. I want to build a project that will do this specific thing. For example, let's say uh, I am a human being and I say, okay, I want a project that turns on the alarm when the sun goes down and it turns off when the sun comes up. Okay, so I want an alarm system based on the day and night schedule. Okay, I could want something else. Okay, I could want any kind of thing I want. But for now, I want that if the sun goes down and it is dark outside, the alarm should go on. It should go off, right? So it should start banging, da 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 da, and stuff like that. If the sun comes back up and there is quite a lot of sunlight available on the outside, then the alarm will turn off. I want an autonomous system. So that's the idea that comes from the human being. So that is the step one. So, okay, you have given this idea. Now, the electrical engineer will start taking the next steps. So, firstly, he, from his knowledge, will take some components and design a circuit. It would be something like this. Okay, he would say, okay, I want to use a sensor that detects the sunlight. Okay, so he would think, oh yeah, I read about the sensor, which is LDR, light dependent resistor. So I can use that. That will detect the sunlight. So if there is sunlight, it would give some specific value. If there is no sunlight and there is darkness, it will give some other value. That way I can detect the sunlight. Okay, so once I have detected the sunlight, all I need to do is to have a speaker, okay, that will sound the alarm and I want it to be triggered at a specific instant, not always. Okay. So I got this LDR and I have this speaker. The symbol of this speaker is somewhat like this, a rectangle, then this curvy slant height shape equipment. So this is a speaker and this is an LDR. So I am detecting the lights, the darkness and the sunlight using this LDR, and I want this speaker to turn on and off. So I just use some kind of switches and balance the amount of current and voltages that would come from the battery. Okay, I learned about that component. It does this and that. So I design a basic circuit. Okay, from the theory, I use these components and design a basic circuit. Okay, this will be doing this, that will be doing this. Okay, so after I have designed this initial circuit, I am going to use a computer to simulate that circuit and observe the output. So I open up a software, I design what I designed initially on a paper. I will design that circuit onto that software and I will turn it on. I'll provide the sunlight. All those options will be simulated in the software. I will check what is the output. If the output is as per my requirement, then okay, great. I'll go to that production step, the actual physical building of that circuit. So far we have three steps. The step one was the idea that will come from the human being. The step two was making the circuit. Okay. Step three was simulating it and checking it. After it is simulated and checked, then we go for this PCB design. Okay, our circuit works perfectly fine. Now we can get the actual components and well, plug them together according to the circuit. So they will be doing what they should do. Okay. And once all of that is ready, we put on a fancy cover and it looks something like this, which you install in your home. And Well, you have a TV remote, you have an AC remote, you have a mouse, so you have a keyboard, you have a mobile phone, and you have a lot of stuff. All of that has fancy covers. Inside it is a PCB. In all electrical component, in all electrical devices, is there is a PCB that looks like this green plate, and the components, the things that are attached to it were designed something like this. They were simulated before they were simulated into a software. They were designed on a paper, and before they were designed, they were verbally communicated by some kind of human being that were was a customer who would say that I want to do this, I want to solve this problem, I want to build something that does this, this, this. Okay. So this is the engineering pipeline, and this is the sequence of how we design the things. Okay, so this is a huge step of designing this circuit on a paper. You need fundamental knowledge to design it correctly. Otherwise, you can design whatever you want on a paper, but there's no guarantee it is going to work in real life. So this simulation will tell you if it is going to work or not, but you need to design it correctly, and to correctly design it, you need to understand the fundamentals of electrical engineering. Okay, so now let's talk about what is electrical circuit. So, uh, like I previously told you, it is something that has some electrical components attached to each other, and they are performing some kind of a task. So that's vague definition of the circuit. Now let's go ahead and see the formal definition of electrical circuit. So it is basically interconnection of components. So all components are attached to each other, okay, and they form a closed path for the current to travel. Okay, so let's say here I have three cell batteries. They're all connected to each other, and and then this red line represents a copper wire. The wire is attached to something called a resistor. We'll see what that resistor is. And then we are again using the wire that is attached to a bulb, a light source, okay, an energy saver or a bulb or light. And that is attached to again using a copper wire. Black line also represents a wire. It is attached to a switch, which is the on-off button that you normally use to turn your lights on and off. So it's the plastic switch. It is attached to that, and the other part of that the switch is connected to the battery. So all of this is a closed circuit, right? Closed path. Everything is connected to each other. Everything. So you start from one point. You can have hundreds and hundreds of components. Here we have three components: resistor, light bulb, switch, and battery. So we can say we have four components and they're all connected to each other. So you can have 4,000 components or 400 components or 40 components or four components. So if they are all connected to each other somehow, then that is a circuit. So this is how it would look in real life. And in the circuit diagram, while designing the process, we use some symbols. Okay, so this resistor, which looks like this in real life, is represented using this symbol. Okay, so there is some zigzag pointy ends, so that represents a resistor. And the light bulb, which looks like this in real life, is represented using this kind of symbol. The switch that looks like this is represented using the two dots connected via a wire. And the battery source is represented using a long line, a long thin line, and a short thick line. So there is one, two, and three. So there are three cells. So we represent one, two, and three batteries. So this is how uh, we define a basic, very basic electrical circuit. Moving on. So I hope you understand the circuit and the basic working principle of this circuit is to transfer energy from one point to some other point. For example, these batteries have a lot of energy and they transfer their energy to this light bulb, which gives light to the environment that it is in. And once the batteries run out of that energy, ultimately You have to recharge the battery or replace the battery uh, to keep this circle going on. So, a circuit is usually uh, designed to attach all components to each other so that the energy can flow from those cells, batteries, or whatever the power source is to those individual components in the required manner. Okay, circuit is designed to transfer the energy to those components in the required form. Okay, so we do understand what is a circuit and it has some electrical components. Now we need to understand these basic electrical quantities, which I am sure that you have heard in your life a lot, especially this voltage and current. You might have not heard about resistance, but many of you would have seen the resistance as well. So we will today understand as well what is this voltage, what is this current, and what is this resistance. So I have included this animation uh, that does represent the role of each entity. So I would say that uh, current is the actual thing. Current is the actual entity that is going to drive everything. Okay. You have any kind of electrical equipment. Current is the entity that is going to drive it. But current cannot do anything without the voltage. So this animation shows that. So the current is this A and P is the measuring units of this current. Okay, so this AMP amps or amperes or amps is or this green body. It is representing the current. So as you can see in this picture, that the voltage is pushing it forward. If the current can't go forward, if the current can't go to the required place, it is of no use. Okay, so we need voltage to push the current. It is the current that is actually going to work ultimately, but without voltage, it can't do anything. So we can think like this that voltage is a tank that has all that energy. Okay. And if it has all that energy, it is going to push some of those electrical charges that it has stored in itself. Okay. So that will go forward and well, turn on the light or the laptop or mobile or whatever it is that you're working on. And resistance is represented by this red body. It is measured in ohms, OHM, ohm. Uh, it, the job of this resistance is to stop this current. So we don't in majority of the time we don't want it, but it is sometimes useful as well. It is inherently always available. There is natural resistance in everything. Okay, so we can't get rid of it. So because of the presence of this resistance, which is stopping this current to flow, we need voltage. Voltage will give it a push. If the voltage is not enough and the resistance is high, the current is not going anywhere. So this rope would be much tighter and this current can't go anywhere. But if no matter how tight this rope is, if this push is so hard, then this current will just move forward. It will just slide between this rope and it will just move forward. So this is the basic relationship between the voltage, current, and resistance. So now I will just say more technical detail. I will give you more technical detail about how these things work. So current is basically flow of electrons, flow of charges. Okay. So there's electrical charges inside anything and their flow. That, for example, there are 10 charges. So there are 10 charges placed here. If they are not moving, there is no current. If they are moving from one point to another, if the charges are moving, then there is current in that place. Okay. Current is movement of charges. So for those charges to move, they need a push, they need an energy that comes from the voltage. So this green body is a single charge. If it is at one point, there is no current. If it starts to move, then there is current. How will it move? Voltage will ensure that it, and the current will ensure the, the resistance of this red body will ensure that it does not move. So this resistance here is depicted by this valve. If we push it downwards, so this flow will stop. Okay. So this shows that okay, this voltage has all these charges, and the movement of this water flow is the current. If it moves, so it is rotating this turbine, which is doing some kind of work. Okay. If we increase the resistance and close this terminal, so there would be not current. So there would be no current, right? So I hope you get the basic understanding of what is this voltage, current, and resistance. You can ask questions about it at the end of the session if you have any confusions about the relationship. Okay, so that was the basic definition of what is voltage, current, and resistance. Now let's have a look at what is the proper exact definitions of these individual entities. Okay, so voltage is basically the electrical potential difference between 2 points. Okay, so I have a wire or I have an element in my hand. Okay, let's say okay, I'll just pick something. Okay, so let's say I have an element in my hand and it has one point here and it has another point here. So there are 2 points of this element that I have in my hand. So voltage is the difference of potential, electrical potential between these 2 points. Let's say I have an electrical potential of 100 on this side, and I have electrical potential of 10 on this side. So the voltage would be 90, 100 minus 10. The difference of electrical potential between 2 points. That is the voltage. And what is this electrical potential? I said, let's say I have 100 electrical potential on this side. It means that there is a huge amount of electrical charges. There is a huge battery which has a lot of charges in it at this point. And there is a very small battery with only 10 charges, very small amount of charges on this side. So there is a charge difference. Okay. So like you can think of it about concentration. Okay, so let's say that if you have a gas trapped in a jar and you break that jar, so the gas starts to move from that jar in which it has huge concentration to the environment. It goes from where it was highly concentrated to the point where it is less available. Okay, so it's the law of nature. Things move from where they are more to where there are less. Okay. So similarly, electrical potential is defined by the amount of charges that are placed there. So those charges will ultimately give you energy. So I have a huge amount of charges on this point. I will call it the positive terminal. And I have a very small amount of charges on this side. I'll call it a negative terminal. And the difference between these charges would be the electrical potential, which is the voltage. It is measured in volts. It drives the current. Okay. So in physics, it is basically refers to the electrical potential difference between 2 points in a circuit or electric field. It represents the amount of energy transferred per unit charge as the charge moves between those 2 points. So I have 2 points. I have 2 points, and I am moving a charge, an electrical charge between these 2 points. So the amount of energy I need to put in to move this charge from point A to this point B is the voltage. The amount of work I have to do, the amount of energy that I need to provide, the amount of work to move this charge from point A to point B. That is basically the voltage. So you can just think of it as a pusher. It will give you the initial push. It will give those charges an initial push. And if those charges start to move, you will have some current, and that current is going to drive whatever electrical equipment that you need. So it is very important that the voltage level should be good enough for some kind of circuit to work in the first place. Okay, so that is why we normally measure. Okay, so I have a ceiling fan. It works on like 120 volts or 220 volts or 100 volts or 12 volts. So every kind of equipment that you use in your daily life well, has some kind of voltage rating. It is as per its design. Okay, so if you give some other voltage to that is recommended, it's not going to work because if you give some different voltage than what is required, there is not enough work energy available to push those charges to flow through the circuit. If there is no charge flowing through the circuit, there is no current. And if there is no current, then of course it's just circuit is not going to work because there is no flow of energy from one point to another. So the voltage matters a lot. It is the first thing, even though it is the current that is actually driving everything. But current is nothing without voltage. So voltage is the most important part because without it there is no current. Okay. So here's the formula of voltage as well. It is the work done per unit charge. Work done for each charge from moving it from point A to point B. That's the technical definition of physics. You don't need to well understand this complexity at this moment. Okay, so correct. Like I previously told you, well, correct. So there are a lot of electrons in metals. We all know that, right? There are a lot of free electrons freely roaming around from left to right to bombardment, and they're all canceling out each other's momentum, and we have no current flow. If there is a piece of metal placed somewhere around you, you touch it, you will feel nothing because all those electrons are randomly moving around and they are canceling each other's effect. So we have a lot of electrons. If they start to move in a certain direction, only then there is going to be current. If they start to move in a circuit in a certain direction. For example, this figure 1a represents these blue dots. These blue dots are the electrons. Okay, these are the electrons. So they are randomly moving here and there and here and there. So there is no electricity flowing, there is no current flowing. But if somehow all these blue charges rearrange themselves and start to flow, like shown in the figure 1b, if they start to flow from one point to the other, from left to right. Now, if you touch this wire, you'll get a small electric shock because now there is current there and they do not flow in a certain direction without voltage. So in figure 1a, there was no voltage applied to this metal wire, but in figure 1b, there was some kind of voltage applied to this metal wire. Applying this voltage made all of these electrons to be arranged in a certain direction and start moving. So this cylindrical horizontal cylinder represents a wire, and all these small red dots represent the flow of charges. So they are all flowing from left to right. They are all flowing from left to right. So there is current in this wire. If they are not flowing, there is no current. They will be there. They are present. They are always present. Electrons are always present. It has always that potential to do something. They are always present, but there is no electricity unless they all flow in a certain direction. Okay. So in this animation, we see that okay, yeah, all of these electrons are flowing in a certain direction. They are not randomly moving. Now there is current flow. Similarly, uh, the below diagram, all these blue dots are moving from right to left. Again, that's a certain direction. It's not a necessary thing that you have to always see, okay, from they should go from left to right. No, any kind of certain direction, if the electrons are moving all together, moving. Moving is the most important part, right? In the certain direction, all of them combined. That is going to produce electricity, that is current, and that is going to drive the components, and it is going to basically this is flow of energy, right? All these electrons had energy. Now they are moving from one point to another. So they're transferring the energy. They're taking the energy from the battery, from the power socket, from whatever power source that you are giving. So they are taking the energy from that point to the other point. So that is the flow of energy. So I included this picture to just I'll show you. Well, we don't see it, but there is electrical current passing through a lot of wires that we use in transportation of power. And of course, it is not visible to the naked eye, but there are electrons moving in these wires. Okay, then there's current. So it is measured in amperes. The measuring unit for current is amperes, and it depends on voltage because voltage is the one who is going to drive it, and it depends on resistance as well because if the resistance is too high, it is not going to flow at all. Right? So it depends on that as well. Okay, so that is about current. Now we'll go ahead and look at resistance. So, resistance, like the name suggests, it is going to resist the flow of electrons. It is going to stop the flow of electrons. So it is going to reduce this current. So all these green dots represents the flow of electrons coming into some point. So if you attach a resistor, so basically that slows down, that limits the flow of electrons. So like there are maybe 100 electrons entering every second, and at the leaving point or the exit point, maybe there was 70 electrons. A lot of rest of the electrons bombard, like you see some red dots here. They bombard with some of the equipment that is placed inside the resistor, and they just lose energy and they don't have any more energy to move forward. So you can think of it like it eats some of the charges, and so now there is less current available. So the job of the resistor is to reduce the current flowing. Okay, because too much current will burn your equipment. So we do need resistors, and we can have some exact specific amount of resistance. We can always have that, and we need these resistors to limit the current because we don't want too much current. Okay, we have a big battery, and that battery has a lot of potential to provide a huge amount of current, but we don't need a lot of current in a very small amount of time. We need very small chunks of current for a huge amount of time. So these resistors play a role at point. So the resistance depends on the property of the material. So it has basically some kind of metal or semiconductor that has the capability of transporting that electricity, but well, it has some resistance naturally. Okay, so in a normal copper wire, all of this flow of electrons is straightforward, going from left to right in a very highly, in a good manner at high speed. But if we introduce a resistor, well, that slows down the flow of electrons, and it eats many of the electrons. As you can see, there are some red dots here. So these are the lo lost electrons. So that is the current. Okay, and the most famous and the most fundamental law of electrical engineering. That is the Ohm's law. Okay, so that is the Ohm's law. Ohm's law is basically the relation between voltage, current, and resistance. So voltage is can be defined as the product of current and resistance. Okay, again, here's a depiction. The resistance is slowing down this current body, and voltage is pushing it forward. So it is the basic law of circuits. It can be applied to linear components. So linear components are the components whose behavior you can predict if you well A switch is a linear circuit, battery is a linear, a lot of different uh, components that have linear behavior. Uh, Ohm's law can be applied to those components, and majority of the circuits in a lot of complex design as well uh, uh, use these linear components. And Ohm's law is the most fundamental and most widely used law in every circuit. Okay, so it is basically Ohm law is V is equal to IR. Voltage is equal to the product of current flowing through the circuit and the resistance of the circuit. That is the voltage. And if you know the voltage, then you can get the exact power source that you require. You can say, okay, I need a 12-volt battery, or I need a 20 volts battery, or I need a 100 volts battery, or I need this or that. Okay, so you can get that from Ohm's law. So if we see what is inside this Ohm law, we can have a look of increasing the voltage will increase the current. That we understand from the intuition as well, because increasing the voltage means you are pushing it more. So more charges are being pushed forward. If more charges are being pushed forward, then more charges are flowing. And more charges flow indicate that there is going to be more current. If you increase the resistance, it will reduce the current because increasing the resistance means it is eating more charges. It is not letting more charges pass. Okay, so here's this well, you can call it a love triangle between VIR, and there's a formula, and the voltage is usually represented by this symbol with circle and a positive and negative terminal, and resistance is indicated by this symbol that we also saw in the previous slides. And current is not represented using some specific component because voltage is a component. It could be a battery, it could be a power socket, it could be something. A resistor is a physical component as well. It is something that has some special kind of material in it. Current is not a physical entity. Okay, it's a theoretical entity. So current is flowing. It is the electrons, which is in everything. Okay, atoms and electrons are in everything. So current is a theoretical entity. So uh, it is there is no specific symbol for this current. This arrow shows that okay, so the current is going from left to the right side. Okay, normally what we say is the current starts to flow from the positive terminal of the battery and it comes back to the negative terminal. So from positive to negative, of course, it is going from left to that right side. Okay, so that is the basic Ohm's law. So let's say if you have a small LED, a small bulb that you can just turn on using some kind of battery. So basically, that is using Ohm's law. So this battery is the voltage. So this is represented using this is another symbol that we normally use for to represent batteries. So this big huge line represents the positive terminal. This small line represents the negative terminal. So this is the battery, which is representing this battery, and we have a resistor here, which is a physical entity. So we include this resistor because we don't want to provide too much current to this small LED. It may burn it. So if we had a larger LED, we might not need this resistance, but for this small LED, we do need this resistor. And this LED is represented using this symbol. So this is a special symbol for LEDs. So it is a triangle with a horizontal line and two arrows indicating outward. So these two arrows are indicating a light is coming from the outward. So this is basically the voltage, this is the resistor, and this is the LED, which we want to turn on. And all of this is a closed circuit. Everything is connected to each other. So if everything is connected to each other, there must be current flowing through this circuit. If the current is flowing, that means the charges are moving from one point to another point. So if we think about it, where were the charges in the first place? Of course, they were in the battery. So the charges are moving from battery to this LED and light waves are coming out. So this is a basic example of how we are using Ohm's law to well, drive a simple LED circuit. Okay, so that is basic Ohm's law. Then comes power. Power is also a terminology that is used along with voltage, current, and power. Okay, so power is basically the measure of how much voltage is used with how much current. So power is defined using P is equals to VI. Okay, and if we want to see how much power is lost, we can substitute Ohm's law. If we substitute V is equals to IR, voltage was equal to IR. So if we substitute IR in place of this voltage, then that is I multiplied by this I becomes I square and R comes to this point. So these the basic version of power in circuits is this P is equal to VI, and we can have this triangle to have all of this different kinds of formulas that you may derive. Okay, so that is powers. It is measured in watts. Okay, so it is basically the power. It is how much energy is being used and how much current is being flow. How much energy is being used for how much flow of charge. Okay, so that is the measure of power. Okay, so then there are some other laws which I believe might be too much for today's lecture. We can go ahead and have this question answer session for the amount of knowledge that we have studied so far, and I will just delay this to our next session. Okay, so I'll just move forward to some of maybe I can see uh, some, well, okay. So I believe we can finish today's lecture to this point, and we will conclude this in 2 weeks, in which we have scheduled our next class because too much information of a new subject might saturate your minds, and there's no point in just stating the things that you're not going to get. So we can have a question answer session to this point.
Okay, everybody, where are your questions? If you have a question, go ahead and raise your hand or write it into chat. I mean, it might be good to give like maybe a little exam. Oh, we got a question from Damian. Go ahead, Damian.
Good morning, and good morning to our presenter and to all our classmates here. Abdullah,
Yes.
thank you for a wonderful presentation. How might we be assessed for this course? I am curious about how we will be evaluated for this course. Perhaps Dr. Lambert could also assist.
Yes, I believe Dr. Lambert can answer it better than me about valuation.
Well, Abdul, let me put it to you. How would you go ahead and test the students? Would you give them problems to solve? How would you do that?
Okay, so from the amount of content that I taught today, I would give the students MCQs exam because hearing about new stuff might not stick in your memory. So if you have some MCQs, they can have basic understanding. They can show you if they understood the basic concepts. So 10, 15 MCQs would be a good thing to evaluate what they learned in today's lecture.
Okay.
That's a piece of hand for me, please.
Let's go ahead and get some more questions in there. I will try to prepare some questions.
So,
I'm going to go into ChatGPT right now and have it give me a problem to solve for Ohm's law, a practical application, and I'll put it into chat.
yeah,
In the
that would be.
meantime, Louisa has a question. If you can ask the question in chat, I will run to artificial intelligence and create a question for testing.
Okay, great. So I gave two formulas in the chat for everyone to solve the question that you would ask.
Oh, did you give one right now?
Yes, I just gave the basic formulas that I showed in my slides.
Let me go back and check. Okay. And then do you see the question from Louisa?
Okay, Luis, go
If
ahead. Good morning,
if
everyone.
electricity is very dangerous, if not the really application. So how dangerous is electricity?
Okay, so yes, definitely electricity is life-threatening. It is very dangerous, but it depends on how much electricity well, you are nearby. So, for example, if you touch some kind of batteries, the DC batteries which have very low voltage and low charge, well, they do have a lot of charge, but if have low voltage, then you are safe. But if there's something with high voltage, then it is problematic for you. Yeah, a human being is also a resistor. Okay, in electrical terms, a
Tanis,
human being is a resistor. It has about 2 mega ohms of resistance, 2 into 10 to the power 6 ohms of resistance. So that's a huge amount of resistance.
check your
So
email.
if there is something with this much resistance, then you need a very high voltage to allow the current to flow through this body. Okay, so for low voltages, you are safe. For high voltages, you are not safe. It would be the current that would actually kill you. But we would need the right amount of voltage to drive the current to you in the first place. So be very aware for everything that has high voltage. Because if you even get near to it, it may fly through the air to you. But that's very high voltage, like thousands of volts, 10,000 volts. Stay away from anything above 500 volts or 1000 volts. So in the household, you have probably have 120, 150, 200, some kind of voltage. That's quite a lot of voltage. If there is anything above 20, 30 volts, just try to be safe. Stay away always.
Okay, so I went to ChatGPT and asked to give two problems to test the student on the equations for voltage and power in electrical engineering. So here's problem one. Do you want to go ahead and read that, Abdullah?
Yes. Okay. So the problem one is that we have a circuit and it has a resistor and there is a battery. And we know the, if there is a battery and there is a resistor and it's a closed circuit, so current must be flowing through it. So we know about the relationship of voltage, current, and resistance using the Ohm's law, and the value of resistance is given, the value of current is given, and we need to determine the value of voltage. So the value of resistance is 12 ohms, the value of current is 3 amperes. So what would be the voltage that would be attached to the circuit?
I guess everybody, you can write your answer into chat. Let me bring up chat. What is the answer? What is the voltage in this problem?
Okay, so as we know that voltage is equal to current multiplied by the resistance. So we have the value of resistance as 12 and we multiply it with 3. So 12 into 3 would be 36, I believe. So 36 volts is the right answer.
And then part B, if the resistance increases to 18, what is the new voltage?
Okay, yeah, exactly. So if the resistance, if the resistance is while the current remains same. Okay, so if the resistance is increasing and the current remains the same, we understood from Ohm's law that if the resistance increases, the current should decrease. But if the current is remaining the same and the resistance has increased, it means the voltage must have been increased. Okay, so but we need to understand how much voltage. So now again we use the same formula, that is the resistance multiplied by the current. So the new resistance is 18 ohms and the same 3 amperes of current, 18 into 3, that would be 54 volts.
So that was a good explanation. If you keep the current the same, but you increase the resistance, that must mean the
Yeah,
voltage has more power to push that current.
exactly, exactly. Otherwise, increasing the resistance should decrease the current.
Okay, let's go to problem number 2 for electrical power.
Okay. So an electric heater operates at a voltage of 120 and draws a current of 5 amperes. Calculate the power consumed by the heater. Okay. So we know that power is the measure of voltage times the current. So we have 120 volts of voltage
Good
and
morning.
5 amperes
Good
of
evening,
current.
David.
So we just simply multiply these two, 120 into 5, that would be 600 watts of power. That is the power consumed by this heater. So you have 600 watts of power. You can have how much time you want to turn on this heater. For example, if you want to turn it on for 1 hour, you can multiply this power with time, you get the energy, and then you can approximate the amount of electricity cost it is going to come in your bill using this resistor heater. Sorry.
And 600
So,
watts is a common amount of power for like a home appliance.
yeah,
Maybe like a little oven or maybe a little
yeah,
heater.
yes,
But if you start to get
definitely.
a bigger heater, start to get up to like 1,000 watts and 1,500 watts.
Yes, yes. So if something is consuming more watts, it is probably going to draw more than 5 amperes of current because voltage is standard in our homes. It is 120 volts, so it is going to remain the same. So the current will change if the power consumption is changed. More watts means more heat.
I know there are people who live off of like or battery storage, and they have a certain amount of watts that they can produce during the day if they have a solar collector.
Yep,
And so they
yep,
try to find home appliances that maybe have like 80 watts or 100 watts or 200 watts.
exactly. Exactly. So if there is someone who's living on batteries in some isolated area, he needs an electrical engineer to design the whole appliance system for them because the electrical engineer would make these calculations and see, okay, I have this amount of battery, so I can have this amount of consumption for light, this amount of consumption for heater, for this. We will tell you, you can have 5 equipments with each with 200 watts. If you want to use more watts, then you need to get rid of one of the equipment. So you have a limited battery.
Yeah, I know that there are people who drive around. They live out of their car or they live out of a van. And so they have a battery with a solar collector maybe on top of the car, or maybe they set
Yep,
it out during the day and collect solar energy. And then
yep,
they have like a battery that stores it
exactly,
and tells them how much battery storage they still have and how much the appliance is using in watts per hour.
exactly. Yep. So those batteries are providing energy for this whole van, and those batteries are going to run out at one point. So the solar panel is giving charge from the solar panel to this battery, and the battery stores its charge. So it recharges itself when the solar panel receives the sunlight.
And it's interesting because some of the solar panels that are built or that are built for like people living out of their cars, they will collect, I think, maybe 100 or 200 watts per hour on a good sunny day.
Yeah. Yes. Exactly. So that's a good amount of energy. But again, it depends on the appliance that you are using. So if you're collecting less amount of energy, then of course you have less energy available.
Okay. Did you get the question from Musa?
Okay, so the
Resistance is
yeah.
used to reduce intensity of energy.
So basically, resistance is used to limit the flow of current. So indirectly, yes, but because reducing the flow of current would reduce the overall flow of energy. So indirectly, the answer is yes, but to be accurate, we can say resistance is used to limit the current, to reduce the current, which indirectly reduces the intensity of energy that flows through the circuit.
So in this sense, is energy power the wattage?
So basically, energy is measured how much power is used with respect to time. We know power is voltage multiplied by the current. There is no factor of time. If you want to calculate energy, you have to include time. So energy is equal to power into time.
Okay, question. Musa also asks, can you indicate the good materials to generate best intense energy in electrical engineering?
It depends on the scale of the equipment that you use. Normally, the hydroelectric power plants, the dams, they do generate a huge amount of electricity. But if you have a solar panel over thousands of acres, thousands and thousands of acres, they might combinedly produce more energy. If you have a wind farm over a whole ocean, it may give you more energy. So it does depend on the scale that you are talking about something, but generally, hydropower plants produce a huge amount of electricity. The dams, which are producing electricity, they do provide a good amount.
And then Pedro asks, are electric cars safe? And are they a good solution for today?
Yes. We saw today that all these electrical equipments are going to get energy from somewhere. Okay, so battery is usually used to provide that energy. So electric cars on itself are very safe, very good. They do not have any carbon footprint or they do not pollute the environment. But the danger part is that once this energy is being flowing from battery to the other points, so there is always resistance somewhere. So whenever resistance plays its roles, it heats the thing up. It heats up. So if the design is not good, someone made an electrical car and a certain kind of drift or certain kind of action that the electric car performed might increase the temperature a lot, and it may burn or it may blast or it may cause something. So if the design is really really good and all possible kinds of actions are performed during the design process, then electric cars are very good and safe. But if something happens, it's going to be a small spark that starts from somewhere. If something happens, there's a 98% chance. If the design is good, nothing is going to happen. Uh, Mostly in electric cars, batteries blast. Batteries are the problem which blast because sometimes the battery you take a lot of energy from the battery suddenly because you need to go from 0 to 100 in 2 seconds. So you need a huge amount of surge of energy. So you take a lot of energy from the battery that does well, change some things in the battery, and with respect to time, if the battery material is not good enough, it may cause harm.
How much wattage is used for an electric car?
That depends on how much, which car you are talking about. For example, if there is a car where that can go up to like 800 miles or 900 miles, or there's a car that can uh, go to for 100 miles, well, it it has a very different range, but normally it can go from like 1,000 watts to like 50,000 watts or even more than that.
Wow.
Yeah, that's a lot of energy.
Yeah. So you need many batteries hooked together. Is that how it works?
Yes, many batteries hooked together, and we use expensive material that can provide more energy in less volume. So those are special batteries.
Yeah, it's amazing that much wattage to move a car for 800 miles. That's
Yep.
it's a lot of power in batteries.
Yes, a lot.
Well, that's going to do it for today. We're come to the end of our time. I don't see any more questions. What are you going to talk about the next time you come?
Okay, so we're going to look into few of the other theorems, and then we're going to see some practical applications of how these things have built, how these laws have built what things. Okay, so we're going to be looking at applied electrical engineering stuff in the next session. Before that, we needed to understand the basics and the fundamentals, so you understand the basic terminologies. And inshallah, the next lecture, we'll see the applied force and conclude this electrical engineering.
Pedro asks, is there any solution in sight to bring down the price of batteries?
As I just told that they do need to be of really good quality, and we require a huge amount of energy from them. So to have a smaller size with good quality and huge amount of energy capacity, you need expensive material and expensive building mechanism. So yes, it is possible with respect to time, but it's a big, huge effort to reduce something that is so good and safe. So it will take time, and but for now, well, they are expensive.
All right. Excellent class. Excellent. So I think that's going to do it, everybody. Do you have any last words, Abdullah, before we close?
Yes, so today we learned about some of the basic fundamentals of electrical engineering, and just think about the stuff that you normally use, and just think about how it is designed and how much effort someone put in getting this technology to you. So before you break it, think about the effort.
Like if you hook up a phone I think only draws maybe 40 to 80 watts. Is that right? Or
Yeah,
less?
somewhere around. Yeah, yeah, that's a good range. Approximate that.
So it's good to think of appliances and how much wattage they're pulling from the system. Yeah, okay, perfect. So
Uh,
we'll come back and I'll let everybody right now unmute your microphones. Where is the, hold on a second. Where is the, here it is. There it is. Okay, now you can unmute your microphones and say thank you and bye.
Yeah, bye.
Thank you,
thank you,
Abdullah.
thank you, and
Bye-bye.
bye. Yes.
Thank you very much.
Bye.
Bye-bye.
Thank you.
Very much, and
Bye.
have a blessed evening. Bye bye.